Hello guys, welcome back. In this video, let us understood one more important concepts in this video. Those are how our ML models before introducing neural networks and after introducing neural networks, and we will also analyze what is feature engineering and how it will be overcome. And we also see we also take an example of text classifier, that is a NaiveBayes text classifier, to explain this. So before going to an example or explanation of this model, let's recap the previous eras as well. In this rule-based systems, actually how we predicted the output, we predicted based on syntax rules. Whereas in this statistical NLP, we take an advantage of probability. In this rule-based system, while using syntax to analyzing that text and predicting the output, we encountered an error, that is ambiguity. So to overcome this, we require to add some more parameters to our code so that to overcome this ambiguity. So during the time, the probability, and by using the probability and statistics, this statistical NLP models came into picture and they overcome this ambiguity. And after overcoming the ambiguity also, some sparsity is still arised. So in order to overcome these sparsity as well, so what we are doing, we require one more advanced model. During that case, these ML based NLP models are introduced. So to overcome this sparsity issue came at this statistical NLP level, we need a best text classifiers. So during this ML based NLP era, best text classifiers have been designed, and by using them, we classified the text as per training algorithm. The features, or you can say, yeah, the features have been extracted here by using that text classifiers. In this ML based models, by using these ML based text classification models. Then here also we are having a requirement of featured engineering. That is, we are manually providing, or we are extracting the features of the given text by using some feature engineering techniques. Like you can say, we're using count vectorized method. It's one of the probabilistic or statistical method where we are using that in order to analyze the features of count of words. In these text classifiers, we are using that. So now that is the issue came, or you can say here also manually features are extracting. So that's why feature engineering happens by using these models. So there is another requirement or advancement is required in order to capture or extract the features automatically. So during that moment, these neural networks concept got introduced. By using these neural networks, this feature engineering got removed. That means the features are automatically extracted from the data that you have given at this neural network level. But at this neural networks, for these neural networks, they do not have a pre-built memory or large memory to remember data. That is, these neural networks do not have the pre-built memory to store the data. So at that moment of time, in order to store the previous data, in order to analyze the current given input and provide you the correct response based on that data, so these requires some additional memory. So during that case, one more concept, or you can say these LSTMs are introduced. What are these? Long short-term memories. These are introduced. So, and after these, so one more era came, that is embeddings based NLP era. Let's understood all these concepts by using some hands-on examples. So those who watched the previous video, they have already knowledge of text classification by using linear regression, as well as text generation by using networks as well as LSTM. Now, in this video, we will analyze a text classification with a simple example, that is a NaiveBayes model based text classification, as well as then we will even understood so how we removed the feature engineering by using the neural networks and LSTMs with taking another examples, and we will analyze how the code will be with a small sentiment analysis example by using this NaiveBayes based text classification method. This is the example of classifying the text between either it's a sad based text or it's a happy based text. You can see these are the sentences that I have taken to feed my model. So which model I am using? NaiveBayes. That from where I am importing? From sklearn dot NaiveBayes. What I'm doing? I'm importing this multinomial NB. This multinomial NB is nothing but your NaiveBayes model. NaiveBayes ML model. Why this is used? This is famous for text classification, only for text classification. You can see these are the sentences or the data that I'm feeding. So I've taken these are the examples, and I've taken the labels to represent which sentence is happy and which sentence is sad. First one, I'm thinking it's an happy, so I provided one. Second one, I feel it's sad, so I provided zero. Like that, I've taken some data with sentences as well as labels to specify which sentence is happy and which sentence is sad. Then, before feeding that sentences data into my model, here you can see I told my model is this NaiveBayes model. Which model? This NaiveBayes model. And this model will accept the data, or this model is trained based on this vectorizer. So what is this vectorizer? This vectorizer is nothing but this count vectorizer. So what this count vectorizer will do, sir? It will count. It will count word words. It will count words. It will manually extract words count feature. So if I send this whole context, then it will capture the word count, and it can assume that word count as a feature. Since we are extracting word count by using this count vectorizer. You can say this as a feature engineering. We are extracting the feature, that is nothing but the word count from our sentences. We are extracting what? What feature we are extracting? Word count feature we are extracting from our sentences. By using what? By using this count vectorizer. Since we manually using this count vectorizer in order to extract word count from our sentences, so that's why we call this a type of ML based approach is featured engineering, because we are extracting the features manually here. So that's why it is called featured engineering. Okay, now we are extracting. So in order to extract the feature, we manually provided a vectorizer. So by using this count vectorizer method, so from where we extracted sklearn features extraction dot text, we imported this count vectorizer. This count vectorizer will actually extract the feature. What is that feature? Word count. Word count will be extracted. Okay, we provided that feature extracting method, and you can see we created our model. You can say we make our model. This make model we have picked from sklearn.pipeline, and what we did, we make the model with this vectorizer. So with this already available vectorizer, that is count vectorizer, and we have taken the model. What model we taken? Multinomial NB NaiveBayes model. So we have taken this multinomial NB model, and what we are doing, we are fitting this sentence and these labels. For these sentences, these are the labels that we are fitting. For these sentences, those are the labels that we fit. Then what we did, we have taken a positive sentence and a negative sentence, and then we predicted by using our model, we are identifying or we predicting the response. Then we are just printing each and every response. So let's run this so that to see the response. I'm just running this. Yeah, you can observe. You can observe here the two sentences, or the first sentence will be printed. What is that? I am feeling bad. So for this, the sentiment is what? It is bad. It is sad. So it is identified correct. Let's rerun it because we provided two sentences. We need to get two responses here. So I'm just rerunning it. Yeah, now you can observe sentence. First sentence is this: I love playing. This is a happy sentence, and I'm feeling bad. So what type of sentence it is? It is sad sentence. Okay, our model got extracted this. So our model, our NaiveBayes text classifier was successfully classifying the text among happy and sad. So like this, you can able to classify your text in real time between happy and sad. Not only happy, sad, you can even use this NaiveBayes model for spam detection in real time. Emails, email system is using these type of ML based models in order to classify your spam mails. That is one of the major use case of this text classification. So you have seen while these ML models got introduced, text classification was successfully done by using these famous models. Those are these NaiveBayes or linear regression. Basically, these are useful for this NaiveBayes is used for low to medium sized data. Low to medium sized data. For large, that is for medium to large size data sets, you can use this SVM, support vector machines or linear regression models. Those are highly suitable for text classification for large data sets. Here, here, so while using these models, one more issue came. So what is the issue, sir? The issue is handling new words. So actually, for these classifiers, you train with some data, right? Yes, we train with some data by using feature engineering method. That is this, we are currently using this count vectorizer method in order to extract the features, right? Yes. So we are using this technique for extracting the feature from the data, from the trained data. We are extracting the feature by using this method, by using this count vectorizer. So this is a feature extraction, so that's why we call it as feature engineering. Since we are extracting the features only from this data, might some words may miss from this data. Let's say if I take the word that is super, let's say this is super. So what type of word it is? It's a happy type word. This is super. And if I try to run this model and try to see the text classification, then let's see what the result I get. You can see, yeah, this is super. So how it is classifying? It's a sad sentence it is telling. But I know this is not a sad sentence. This is a happy sentence. Why it is classifying this as a sad sentence? Because so while while training our model, while training our model, we haven't provided that sentence. We haven't provided that sentence related context, and this features extraction also not happened by this count vectorizer for this new word that is a super. For this new word super, this feature extraction was not happened. So that's why it was unable to predict that word as a happy word. So this becomes one of the issue here in real time. This becomes one of the issue. So what is the issue? Unseen words may confuse the model and lead to poor responses. If I provide, if I provide this as well, like if I add this sentence as well in my data, and if I provide the label as well for this data, now it can able to predict the correct response. You can see currently it is running. Yeah, you can see this also happy type sentence. This is super, it's a happy type sentence. So like that for every for each and every data, we cannot able to train in real time. During that cases, so what happens? Unseen words may confuse the model. So whatever the model that we pick, for that model, either it may be NaiveBayes or linear regression or SVM, support vector machines. So whatever the model may be, unseen words, that is the data we haven't trained that model, those may confuse the model and leads to wrong responses or poor responses. Here you need to understood one more point. We are training our model from scratch. By using what data we training our model, through that data only our model is responding. That's it. We're training our model from scratch. So here the major issue we face is manual feature engineering, manually extracting the features from the data. So this leads to create unseen words and may cause confusion to our model, so that our model may predict wrong responses for unseen words. While handling new words, our model may not predict the, the response correctly. Or let's understood this feature engineering. Let's understood this feature engineering with a small real-time example. Imagine you have a toy box full of different colored balls. Like you have a red ball, you have a green ball, you have a blue ball. And you need to group them based on the colors. So traditional ML models, if you take traditional ML models like support vector machines or this NaiveBayes or linear regression model, we need to manually tell the computer that this particular ball color is red. So group them to red. If it is blue, then group them to blue. So like that, we need to look at the ball color, and if it's a red, group it to red, and if it's a blue, group it to blue. Like that, we need to manually tell. So here in this example, we have taken or we considered this count vectorizer. It will count the word frequency, or you can say word count. It will extract the word count as a feature. This is manual work. This manual work of telling the machine which extracts like a color, size, or texture to focus on. So that we can say as feature engineering. So what is featured engineering? Telling the machine which features, which feature to focus on. Telling the machine to which features focus on. So features are like you can say for the current example, what I have taken like color, right? So if we have three balls, then based on the color, you can classify, or based on the size of the ball, you can classify, or texture of the ball, you can classify. So like that. So the if you are manually telling the feature on which you want to classify, so that's we call it as a feature engineering. If you observe in this text classification by using this NaiveBayes or linear regression models, so till now we have seen, we have manually told it. We have applied this feature engineering. That is by using this count vectorizer. You can observe here under NaiveBayes. Under NaiveBayes, you have seen this count vectorizer we have provided, and we have told that to extract this feature. You can see, yeah, we provided that vectorizer. Now, if you open this logistic regression also, in this also you can see we have provided this count vectorizer, and by using this count vectorizer only, that is we have specified that as a feature. So that feature you can able to extract, that we have told. You can see vectorizer dot fit of these texts. Yeah. So like this, we have provided the feature in these traditional models. So we have, so when we introduce this type of feature engineering, when we extract the features based on this feature engineering, so there we are facing the issue of unseen words or new content classification. So we have a requirement to overcome this featured engineering in order to overcome new words classification, new text classification. There comes an approach, that is a neural network. There comes the advanced advancement of these current ML based models, that is a neural network models came. Now let's also understood how these neural networks will help us to overcome or to understand the new text. So let's consider with the previous example, like we have a box with red colored balls, blue colored balls, and green colored balls. So how these neural networks will overcome that, or how these neural networks will classify that? These neural networks are like super smart robots. What? Super smart robots. You don't need to tell them what to look for. They can learn patterns and important features on their own. If they see the colored balls, they learn red balls belongs together and blue balls to belongs to together. These robots figure out what matters. Either it may be what feature which matters to classify the data. without need you to explain what feature you want to extract. This is one of the example for classifying the text among happy and sad. Now you can see we have imported the model from TensorFlow Keras models. This is this is the sequential model. I'm importing this neural network model in order to analyze my text. Now we are not using any text classifier. Here we are using ML based neural network. That is, this is sequential. By using that model, we are classifying our text. So I want to tell you one more point here, that is these models, these ML based neural network models will take input only through vectors. It will take input vectors as well as it will provide you responses as well in the form of vectors only. So before we are sending our sentences, or we are sending our training data to these models, or before sending our sample data to these neural network model, we need to convert our data into vectors. At first, we need to convert our data into vectors. Then we will send our data to these models in order to extract the features or in order to classify the data. Now let's see. Yeah. So now let's take the example. I'm picking the same example of happy and sad based text I'm taking, and I provided labels to specify this data represents these feelings. And you can see I've taken a tokenizer. This tokenizer I have taken from, you can see this tensor flow dot keras dot pre-processing it text. I've taken this tokenizer and I have loaded this tokenizer with the number of words, that is 100. And now I'm fitting these data as text. I'm fitting these text data into my tokenizer and converting that text to sequences. By using these sentences, I'm converting that text to sequences. Then I'm storing the data in these sequences. Now our sentences got tokenized. Then I'm applying a specific length padding to my data. Before passing the data to our model, we need to apply the specific length padding. So that's why we applied the padding as well. Then you can see we initialized our model, that is sequential of, and we added for our model, we added the embedding parameters, and we added some memory, and we added some dropout. We added the dense model as well, dense as well. Then by using all these parameters with our model, what we're doing our model, now we are compiling our model with this optimizer and loss and matrices. Then what we're doing, we are training the model. You can see model dot fit. We're training our model with the padding sequence, whatever the padding sequence that we get from our sentences. By using these sentences, we created a tokenized sentences, and that tokenized sentences we use it to create the padding sequences. Now we are using that padding sequences in order to train our model by using this dot fit, and we provided the input sequence as well as the labels. Since any model, any ML based model, any neural network model understood only numerical values, that is zeros and ones, or any numerical values, these models will understood, but these models do not understood text. So that's the reason why this sentence is tokenized. So whenever it get tokenized, that means that this text will be converted into vector format here, and that vector format is in the form of numerical values. and that vector format data we are passing into our model. These are the word-based vectors. And this is nothing but the labels are nothing but the output predicts that we passed. These are obviously numerical values, so we don't need to classify or we don't need to convert them into vectors or numerical values again. So that's why we're passing that data. Now we're passing our padding sequence in tokenized format, that is vectorized format, and our labels in numerical format only. In the same format we are passing to our model and training our model. We have trained our model with these many epochs and verboses. Then now, so for predicting the sentiment for new sentences, we have taken, we considered two sentences as an example, and by using the tokenizer, again, we converted this data into tokenized sentences. You can see I converted these sentences into tokenized sentences and I applied some padding to it. Then after we are passing this data to our model to predict. So model dot predict of this new padded sentences that I'm passing. It will predict the predictions, and now we just printing the responses. If the prediction of 0 is great, if the prediction value is greater than 0.5, then we are considering the sentiment is happy. If the prediction value is less than 0.5, less than or equals to 0.5, then we are considering the sentence prediction will be sad. So now let's run this ml dot. Yeah. So the same file I'm running here. It might take a second or few seconds in order to create this neural network model with specified parameters and train with this data and take these questions and provide us the responses. You can see we got the responses. So what we're getting, I love playing. It's a sad sentence and I'm feeling bad. So it's a happy sentence. Why our model is telling wrongly? So let's rerun it to observe. I think our model got confused. So again, let's try it. Yeah. So I love playing. It's a happy sentence. And I'm feeling bad. It's a I'm feeling bad. Yeah, it's not a happy sentence, but it is telling happy. I think our model extracted some other features, so that's why it was telling like this. Now let's rerun it so that we can able to extract the correct features. So I'm just rerunning it again to see the response. Yeah, now you can see it was predicted correctly. That is, I love playing. It's a happy sentence, and I am feeling bad. It's a sad sentence, right? Yes. So now our model got predicted successfully. So previously we need to provide what feature we need to consider. So that we are manually telling. In previous approach, that is a NaiveBayes model text extraction. But during the case of neural networks, do we told anywhere take this feature? No, we haven't told or we haven't manually told to our neural network model to classify the text based on this particular feature. We just provided our data and we converted our data into tokens, that is the acceptable format of our model, and then we just taken our model and we just loaded our model with our data and we provided some questions and we predicted the responses. That's it. We haven't provided anywhere the featured engineering, that is this feature you need to extract. But in NaiveBayes, you can see here we have provided this data And we are telling this feature you need to consider to our model. Here you can see for this model I'm telling this feature you need to consider, that I'm telling in this NaiveBayes model. And then we're providing the questions to predict. So this feature engineering got removed in this neural network era, neural network phase. So this is how our neural networks or LSTMs overcome the issue of this featured engineering. So let's take a comparison between this ML based era, right? Yes, the ML based NLP era it is. This all, that is this text classifiers introduction, or our neural network models introduction, or LSTM introduction. This whole thing happens in this ML based era. So now let's look at some basic comparison between these NaiveBayes models or these text classifier models versus these neural networks with LSTM. So comes to the featured engineering. Since this is the thing that was overcome by this, so let's consider with it. So coming to featured engineering, in this text classifier like a NaiveBayes models, manually we need to tell which feature you need to extract. That is a bag of words that we need to tell in this NaiveBayes model. Whereas coming to this neural network model, the feature engineering it's automatic. So after introducing this neural network, now the feature engineering becomes automatic, and it learns patterns or it learns patterns and relations via embeddings. You can see, yeah, I've mentioned those as well. So to make it visible, yeah, let's zoom it. Okay, now let's understood one more. Let's take consideration of one more comparison, that is context understanding. Do these NaiveBayes models really understood the context? No, this will focus on the feature that is extracted, and these models will classify the text based on that features only. Whereas coming to these neural networks, since these are understanding the features automatically, these are capturing the whole sentence patterns, as well as these are understanding the whole sentences. The understanding will be there of context in this neural networks, whereas here that understanding won't be there. So coming to, let's say if I provide new words, so while training I have not provided that words, but new words I have introduced, then how these NaiveBayes models will respond and how these neural networks will respond. You have seen these NaiveBayes models are responding poorly. That is, unseen words may confuse this model. Coming to this model, coming to this neural networks model, it can able to betterly respond because embeddings can help with unseen words. So that's why these neural networks can able to understood and can able to respond to unseen words as well. Coming to complexity, these are simple, that is a NaiveBayes models are simple. Coming to this neural networks models, these are somewhat more complex and require more training as well. So that's the major comparison between NaiveBayes models and neural networks models. So whenever these neural networks came into picture, that becomes a big game changer of these ML based models. So before neural networks, our ML based models are like this, and after neural networks, our ML based models becomes much more efficient with LSTM and can able to overcome the feature engineering issue, and understanding the context issue will be overcome after introducing these two, that is the neural network based models and LSTMs in ML based NLP models. So while explaining these neural networks based models, I provided some input to these models, right? For training or for predicting the response, I provided the input question that is provided by the user to these neural networks. So how I passed the data to these neural networks in the form of tokenizers, nothing but vector format data that have passed to these neural networks. So how our neural networks will actually understanding the text? By using the vector formatted data. By using that data only, these neural networks will understood the word meaning as well as the word patterns, the sentence patterns, as well as the relationships as well. Like that only, by using that vector data only, our models will understand the relationships as well as the patterns and the word relations. So there will be a requirement there will be a requirement in this ML based era to represent the text in the form of vectors. So while ML models are introduced, like these models are introduced, so there, how we considering the text at these models? We considering the text in the form of vectors, right? Yes. You can even consider the previous example. So here, if you open the neural network based, so here you can see, yeah, this is the input that we provided. So this is the input that we provided to our model, right? Yes. So if you print this padding sequence, then you get, so then what you get? You will get vector formatted data. So first I want to show you that. So let me comment all the below sentences and yeah. Now I want to print this padding sequence. So whatever the padding sequence that we send to our model, that I'm just printing. This is nothing but the padding sequence, right? Yes. And let me provide a string as well in order to understood that as a padding sequence. So let me run it again so that this padding sequence, how the data will be, how the padding sequence data will be. So which type of data we are sending to our model, that let us understood by printing this. Actually, so since we are using the tokenizer to convert that into tokens, you can see how the data will be. The data is okay. The data is actually in the form of tokens. Yeah, let me rerun it so that you can able to observe clearly. Here actually, since we are using a tokenizer to convert that into tokens, you can see how the data will be. It will be a vector, nothing but a array of integers, array of integers. That is nothing but a vector. Our models will understood only these vectors. Our models don't know this text data. We can understood this text, but what our models will understood? Our models will understood only this numerical data. So that's why first we are taking the data, then we are tokenizing, or you can say we are converting our data into vector format. This is nothing but a tokenization or embedding. Then we are sending this data to our model in order to train our model or ask the question to our model. Due to our ML models, nothing but our neural networks require vectors from words. Words are nothing but, it may be training data words or the question words that we providing to our model, neural network model. So from those words, since we require vectors in order to send the data to this neural network or ML based models to understand sentence words or sentence meaning, we need embeddings. We need embeddings. So these embeddings based NLP era came. Here, majorly some embeddings got famous, and that is the reason why these embeddings era came. The reason for this is since we require vectors here. So to pass the input to our neural networks, we need vectorizers, that is word to vector converters. So that's why there is an emergence or there is a evaluation of these embedding based NLP models. This word to vector conversion requirement lead to creation of some embedding models. These also revolutionized our ML models, ML based NLP models a lot, that we're going to introduce in next session with some more detailed examples. I hope this video is useful and you understood a lot more concepts here like NaiveBayes, text classifier, and neural network concepts and LSTM, adding LSTM to neural network to enhance or to overcome this feature engineering issue by using this combo, that is this neural networks and LSTM combination. You have understood with some example code, and I hope you understood how the model ML models will be before introducing neural networks and after introducing neural networks, and you also understood the requirement of vectorizer, that is you can say embeddings based NLP era. The reason behind this is we need to convert our word to vector because these neural network will analyze only vectors data. So that's why we need a word to vector converter. So that's why these embedding based NLP era requirement is there. And during this era, this provided some more embedding based NLP models to advance the available neural networks and LSTMs to produce some more efficient results. That's it all about this video. I hope this video is useful. If you feel this video is useful, then please like, share, subscribe, and hit the bell icon to get the latest updates. Thanks for watching again. See you back in the next video with another interesting topic. Until then, bye bye, guys.